I think 4 months ago, John asked me if I would speak to a few of his colleagues in the last year. And we saw this morning, so it's great to be here. Just so I can take a poll, get a sense of the audience. Who's, would you say, is a computer scientist or computer science background? Raise your hands. Biostats. Okay, electrical engineering. Any electrical engineers here? Maybe you should. And then clinicians. Okay, great. Well, I think, this chart here is why I made the jump from Lockheed to Penn. It's these three areas that are three kind of things that are occurring that are entirely exciting to me, and set the backdrop for a lot of choices that we're making on the data science side and operations. And one is the healthcare market is changing so that there's this alignment with patient outcome, with cost and value, and we're seeing more and more of that come in material this year. It's really exciting, and that's really that kind of market demand is what can give the momentum behind data science solutions and operations, and it's really required. The other one is the best technologies are open source. So I'm sure I can get into debates with IBMers or folks at Lockheed Martin, but today, me and four other guys in the garage can do what only IBM and Lockheed could do 5 years ago, because the best algorithms are out there for everyone to use, reveal tremendous open source frameworks to apply, and really poses you to the next step that you're beyond that. And then finally, I see this over and over again, the best solutions, the ones that leave the least on the table, are where you have the data scientists talking and at the same table with the clinicians and working through things. So for example, when I was at Lockheed working with Penn, we were asked to do type sepsis. Really, that's easy. 0 or 1 sepsis. When I come in and start to really have the conversations where our interests are clearly aligned, there's no barriers, it's very complex. It's a whole halo of things that we want to get into. And it's an evolving conversation, it's an evolving solution. It's incredibly important to be in the team and be doing that. So these are things that my bias and background kind of help direct me in these different areas. So just real quick on the kind of products we create, we try to move up this value chain. I think maybe a year ago or even now a bit on the operations side, folks think of data scientists as data analysts. When you just want to pull data and tell me, is the arrow going up or not, is the Pareto chart out. But really what we're about is building data models where there may not be a theoretical formula to describe the model, but going to generate that data model with the data. And we could create analytic reports through pattern recognition, to self-discovery systems. We look at this, determining when something is moving up or down, like mortality or procedures more deadly, and what might be correlated with that. And then the top one, which I think gets into really a step function delivering care, are predictive algorithms or algorithms that detect things that are hard to detect clinically for the clinician at the point of care. And that's really where we're working and focusing. And so it's about bringing all this data to bear. So in that first statement about the market's changing, where you're trying to allow the value to connect to the outcomes to connect to the cost, allows us to get drivers to say, you know what, it's worth getting our algorithm just 2% better because that will yield this in outcome for the patient and this in cost. And so this is kind of just a cartoon, of course, looking at accuracy, reliability, latency, and throughput from the viewpoint of real time, where if you say reliability, if you're below a certain point of reliability, it has no value. If you're a little late with the message on latency, the value greatly declines. You can say that someone has septic shock, but if they're dead, then it's no good. Right? So you need to deliver at a timely manner. What is that timing? And understanding how all those pieces come together. So if we're going to do feature engineering, we're going to compute or fill the missing data, the accuracy of that missing data is going to affect the accuracy of the model, which then affects the ability for the clinicians to deliver the care, which affects the outcome of the patient. So there's kind of this known graph, or this kind of axis connection between all these things that we want to understand of data. It goes back a long, long time. And for the most part, it's all there. The IS team has worked hard to, one, make a gold standard, two, make it accessible. And these, I think there probably are some more. But Penn Data Store is a data warehouse. There's like, I think, it's between 12 and 20 different data sources that feed into it. It's refreshed every day. Latency is between 1 to 2 days. The quality data mart is the enterprise view to that. So how does the quality team, the executives and the directors, how do they track how they're doing all these things that the hospital will look for? That's the dashboard. Then Pennomics and Penn Seek get into a little bit of self-service for researchers, I think geared towards clinical researchers, saying, what is a cohort, a good cohort of patients that fit, X, Y, Z definition. So Pennomics, and who's worked with Pennomics here? 1, 2. So it's available, and you get access to it. And they're starting to pull in some genomic data. They have a complete, maybe a caveat on that, but nearly complete export of data into it. I believe it's de-identified. You can get it down, you can say yes. And then Penn Seek is very similar to that, except its focus is mining the text data in chart information. And for Penn, that's predominantly on outpatient, but they're making this as in text form. That's why we form is going to be looking through and pulling that. So what's my job with this backdrop? The data's there. What's the big deal? Well, for me in data science, my realm is in numerology, statistics, and real-time applications, and putting those things out. And I think on the research side, about statistics, computer science, electrical engineering, you want a matrix, you want vectors, you want to apply quantitative methods on big swaths of data. And looking at a relational database, we're trying to manage all these different joins and what data are you missing, and INR is different than inpatient, which is outpatient, and all things are difficult to work through. And ultimately, you want to get to this matrix of data to start looking at statistical relationships between it or data model decision boundaries in that data set. So for me, when I came here, this is kind of, I thought this would be a great data set to then use as signals, so to speak, to feed into what we're trying to do in that framework. And my goal is to quickly deploy these kinds of applications, whether it's detecting sepsis or remissions or detecting someone's heart failure, but along the way provide tap points for researchers to come in and explore the hard problems, but in a way that fits into our framework ideally. Because if some great finding is made, I would love to pull that in operations as appropriate, which would be a really great win. But at the very least, we're allowing the researchers to really kind of continue the boundaries of what's understood and known. And in data science, in healthcare, that has a lot of unknown. So I really am trying to enable that as much as I can and would love feedback. Wherever I'm pointing now, I'm sure there's some adjustments. I know there's some adjustments we need to make. So just quickly, our team, we have 5 folks that report to me, and I kind of have them focused on different areas within the health system, although back in the team, we kind of triage and build off the same set of tools. And the kind of products that we build are these real-time detection and prediction solutions, as well as these analytic discovery reports. So real-time detection and prediction solutions, that could be time series. This person is going to have acute illness in the next X hours. It could be the hospital's going to exceed census in the next 24 hours. It would be a very different kind of problem. To this image appears to have a tumor in it. Those are all kind of different categories of problems that we want into that set. To this analytic discovery reports, boy, we're seeing a rise in readmissions. What's going on? Why is that? There's a spike in deaths in the ED. Why is that? And seeing if the data can lead to some hypotheses that clinicians can really run down. And so 2015, this has really been our focus. We've gone through some iterations in our framework in attacking these kinds of problems and talking with a lot of people to change the culture in understanding how to work with a data science team, having us learn how to work with the clinical side. So on that side, working with the clinical team, a big part of it's in setting up the discussion and letting the clinicians know that they're a part of the design process. And it gets back to how do we connect our performance with their needs and using those as tuning factors. And just to put this very quickly, this comes from our design sheet that we go into with each of these new problem sets. But it's really around what's the event we're trying to connect to, and defining a time zero for that event, whether it's an acute illness or it's heart failure or readmissions. What's time zero? And this is a good culture thing where we're trying to explain to the clinicians how a label for an event is different than the set of data that we'll use to predict that event. So whereas we might define sepsis as someone who's coded as septic, and the time that they're septic would be maybe lactate is above a certain value, blood pressure is below a certain value. If we use those to label that event, we're not going to use those variables in our prediction. We're going to use something different. And so it's this, and the labels are really where we start to encode the brain of the clinician into the data to optimize our decision boundaries. And of course the timeline. This is interesting to get into where, what if we could predict acute illness 24 hours before, we talk about respiratory failure and severe sepsis, and the clinicians are saying, well, I don't think I would do much. We would just put this person on high alert. Perhaps it's within 6 to 12 hours. Now I'm getting ready to deliver a bundle to change the trajectory of the patient. So those are really interesting to predicting readmissions when someone's scheduled for hip replacement. At that point, predict once they get the surgery, how they can be readmitted. When does the clinician want to know that? Well, they want us to know when the person will come back into the pre-op labs. So getting into those kind of conditions really helps design how we're looking at the data and processing it. Visualization. This is, I think, an area of visualization is maybe not the best way to characterize that. But the question is, we can build it, biostatisticians in the room, computer scientists in the room, when you build these models, you can build really powerful forecasts or really powerful predictive models that obfuscate why they're making that prediction, right? So when you get an output of a random forest, it's not a probability, it's the threshold value that you train to. And it's hard to say that the variables you put into that have had a certain percentage connection to it, right? So you can use a logistic regression that gives you a probability of output, that tells you what components that you put into it, how they contributed to that prediction. But the forecasting power is typically not as strong. So we're in this kind of interesting place for delivering clinical care. Do we take the model that's more descriptive of the situation, but not as strong a predictor? Or do we take one that's a very strong predictor, but isn't as descriptive? Which one is going to be more actionable? And this is something we really have to go into and explore. I think it's a great area for research. And then measure the pathway. So this gets into what are we doing. So in building these applications, we're putting a system in place that's more than just a machine. It's more than the algorithm. It's the machine connecting to the person-human machine interface and the outcome of the patient. And so we got to measure that whole thing. So when we put out an alert, what's the actions of the clinicians? How often they're going down this understood pathway, and what is the outcome? And while you measure that whole system in that way, you'll start to understand where your initial hypotheses were wrong. You have to make adjustments. But it's looking at that whole piece as opposed to saying, we're just going to do the best job we can. We're going to give the clinicians the best information they can, and we're going to do their job. I think that's not where we want to go. We want to understand what the idea or the pathway for the clinicians are and give them that feedback. That doesn't mean we don't do it. Sometimes it's just tough. And we have to, I would say, retreat to the point where we just give them the best information and let them do what they need to do, not knowing what that might be or what the outcome should be. But I think that's the way that's going to retreat to. Patient outcome goals connected to that piece. And the other one is false alarm rate. How many false alarms do you want to get the true positive? Is kind of a tuning now in what we put into it. So the pieces to this workflow. So this is getting into kind of like under the hood of building these systems. I think these are the pieces when you're doing research in exploring a model, as well as doing application development. It's not a surprise. It's extraction, cleaning, feature engineering, and model fit. So this isn't going to win me any patents or awards to look at this. So the thing I want to highlight is, ideally, these are pristine things. They're not coupled and integrated. But always what happens is that when you don't think about these things, you're like, okay, I'm going to pull this data, but I don't want all the diagnoses. So we're going to group them by some category, some cancer category. So I'm going to just go ahead and do that. I'm going to do a little feature engineering up front. And actually, I know I want to resample it. I know I don't want just these things kind of feeding. I resample every hour or every day because I'm trying to predict readmissions. So, okay, but I'm still good. There's not a problem. But wait a second. Okay, now that I get into the clean phase, and I say I want to have a new kind of resampling, I'm going to do some kind of time series analysis on my data. Because it's just more operationally efficient if I do it in this clean phase. So now I'm going to keep going. And now in feature data, well, actually, I forgot to pull in this information that I want to use, right? So I'm going to pull that in, and I'm going to keep going. And so now I'm kind of feature engineering-ish. And then finally, the model fit, you go down the same path. And so what you have is, at the end of it, potentially a very successful outcome from a research perspective. And even from an application perspective, you can just knock the socks off whoever will end up on New York Times in headlines. But we want to maintain the system, and you want to understand the effect of feedback that you're getting from some of the inherent data. It becomes a very coupled and brittle system, and effectively it becomes this black box. You have big technical debt. And furthermore, if you came up with a wonderful algorithm, a new way to process time series data, well, it's connected with the Twitter data you're feeding into it. You kind of let the domain of the problem and the specific problem seep into all of these pieces, whether or not it needed to. And at Lockheed, we had our group in Cherry Hill that we worked with DARPA. This would always happen, where they're brilliant, they're solving the problem in computationally a great way, making the customer really happy, and then we want to bring it to operations. And there was this trough, they called it, of research to operations, where it just did not happen. For a lot of reasons, not simply this, but this is definitely a piece of it. And furthermore, my job at Lockheed was to take wonderful algorithms and apply them to different domains. And this was my enemy. And I really tried to create a standardization, a framework standardization that would protect ourselves from that, and at the same time not get fired. Because people, you hear this, you tell your best minds, we're gonna like lock you down. We're gonna we can do your feature engineering this way. You only do it this way, and you make a standardization, and so now it's a new standardization with a whole swath of groups that came before you with a great idea. And so what I mean by standardization is just internally. For what we're doing, we're just going to call cleanness. We're going to call feature extraction a certain way. And we're going to allow people to tap into it and do whatever they want in their box. So they know when they get something from us, it means that only so much processing has been done to it. It's very self-contained and clear. And if someone hands us back an algorithm that detects sepsis in a wonderful way, and all they want is the real-time API we're providing, great, right? But if you did anything inside of it that we might want to repurpose, it's probably going to be a big pain in the butt. So it's not as bad as it sounds. And we have these principles to kind of help us along the way. So there's no panacea for the framework and standardization. In my time here, I've looked at where I thought the biggest bang for the buck would be in terms of the classic problems. There's time series problems, there's natural language processing kind of problems, there's image processing, a lot of different ways. You can like force them all into one mold, but you're making many, many compromises. So what I decided to do was focus on time series. So looking at acute events and longitudinal events as the object of the patient as they move through time. And it's not too painful to do it that way. So decouple the design and the problem in the domain. We'll talk about that in a previous chart. But the other piece that's very important to me, that's can be hard to do if you don't set out in a purposeful way, is to make the desktop version, what you might use at your desk, be equivalent in form an interface to what I'm using in real time. And so we worked really hard on doing that so it's not hard for you. So once you develop an algorithm that works for our interface, we can just say you plug it in real time without much effort. And so we worked really hard on that. The other one is encapsulating self-describing data. So this is a big deal for me. I've seen it really be successful in a lot of different domains. And that's if you want patient data, and if we're looking at time series, and we can just deliver you a matrix and a vector with some metadata on top that is simple, clear, self-contained, self-describing, it's going to go a long way. It's going to be very easy for you to use. It's going to be easy for us to take your output back into our system. And so that's another focus. And then finally is holding the interfaces to allow internal flexibility. So we just have our tap point. That's the price of the framework, right? We have our tap in and outs, but you allow the flexibility to do whatever you want inside. So I'll go into the cartoons on this. So I think if you look at data every day, you deal with matrices, you do an algorithm, say a method that's statistical work, you're often looking at matrices, you're often looking at things that are changing in time. I just want to give a sense of what the machine sees, what we're producing. This is a set, this is for one patient in time, in one encounter, with the highest, most frequently measured set of vitals and lab data. And this is what the machine sees. So blue is when there was no measurement. And then the spectrum here is just all normalized. It's not particularly meaningful other than to say that there's data and the data is changing. But what we do is we work for every encounter for a patient to create a payload. I guess I'm infected from my previous job. We have this payload of data that we encapsulate into the self-describing data that has all the information that Penn Data Store has for that patient. So it's going to be the vitals, the lab data, the orders, the medication, et cetera, et cetera, et cetera. So you can see this thing becoming very large, very sparse. So we're doing a few tricks to manage that, but basically that's what you're getting, right? You're basically getting this very sparse matrix with a lot of rows that's set up for you to start to apply some R methods or some Python methods. And then alongside here are things that you might want to label. So when they're in the ICU, when they have quote-unquote sepsis, and so we have methods for you to apply different labels to that. That's a flexibility that you have. So here's kind of the cartoon of what we're doing. And the boxes here are, you can think of as what, those are the processes, arrows are the data flying through. The boxes are what you might create as a researcher. You could say, Mike, the data at ingest, we're taking all that data in where we create the output of that is a patient metadata that describes who they are, a little bit into that, and then that payload. And you say, just give me that. I'm going to do everything else. I don't care about all the cleaning you're doing and all the other tricks, and that would be great. We would give that to you. And what you would return back would be any number of these things. Maybe it's just the output, right? The label, the particular you're producing. But I think these are the kind of the domains of research that encompass these spots. I mean, and ingest, after ingest, it's the raw data. Can you learn from it? Is this significant? Are there interesting things occurring? And it's really untouched. To the cleaning, that's where we make some choices about data imputation, some common ones like global filling, extending, resampling, really easy to manage. But you still can ask those fundamental questions of it, just kind of easier to grapple with. To the feature extraction, so this is where feature extraction would be perhaps you have this high-dimensional space, and you want to project it down into a lower manifold, like a principal component analysis or some nonlinear methods. That's perhaps where you would do that, and a lot of really great research to be done there, and I can only that modern signal processing, and then to the model fit. So what doesn't fit here very well is, I would say, patient flow. And where the object isn't necessarily the patient. It's not the patient flowing through this, how they are changed and sampled over time. To patient flow, really the object is the hospital, right, and the units. So another thing that may not fit this very well is single image processing. You can think about ways to put it in here, but This is really focusing on time series. And so we have both data sets going into it, Penn data store done every day, and then real-time API feed going into it as well. So this is kind of a picture of the data standard, and it looks the same no matter where you tap to it, but it's just different things are done. So there's the abstraction, which that is a point to be not laser, but I'll use some laser. So this is the abstraction, so to speak, where I haven't told you how you're going to access it, what it looks like in memory, what it looks like on disk. It's this schema where we have just basic patient information or population information, and then statistical summary of what's there. So if you want to grab all patients that had an INR value, or grab patients that had an echo or whatever, then it would be easier for you to do that. And then inside here is a payload that has the discrete data events over time that you would pull and actually do your learning and processing on feature extraction. So this data we pass through in real time. We just update that, and anytime there's an update, we process it and do it in real time. Or you can do it as a batch. Say, give me all patients that died in the last year. Then to the data container. So again, open source is where we're staying. There's kind of our operational flow, how we bring everything in. This is what you would call a NoSQL construct, and we do that because we're dealing with large-ish amounts of data. I mean, it's on the order of 100 gig, which isn't what Google would call big data, but it's a pain to manage on my laptop. So we deal with that here, but it also, I mean, it provides a lot of flexibility for this kind of container. It's difficult to put this in a relational database where it's each patient data is self-contained and easy to extract, where each patient data is totally different, and you may want to change how you represent that, etc. So because we're using something that's unstructured for our table information, we can accommodate these different tap points for the data set with the same schema. In memory, we use Python. Any Pythoners here? Okay. R, we use R predominantly. More hands. Okay. That's another So R has this constructed data frame that Penn has completely stole, and it's incredible. When I first started using this, that's when I realized that you don't need locking right. It's an over exaggeration, but myself, who becoming less and less connected to the technology, I was able to do what I would have 4 people work on for 2 weeks in a city. So it's tremendously powerful there. And then this is what's in memory. And then when you say, Mike, okay, I kind of buy into this, or maybe I don't, I want to just kick the tires on it, give you some data. What I would want to do is give you something called HDF5, which is a standard out in the scientific community. It's very big in particle physics, very big in DoD. I'm not sure how many folks use it, biostat, but it's basically optimized for whole matrices. It's self-describing. It can get really big. It can get on the order of tens of terabytes for a file, but still managed very easily. It's a great tool to use. Machinelearning.org that promotes free open data, holds data in HDF5, and there's a lot of examples of points out. So it's a good set to use. Or we can use CSV files and just dump that out, which you would lose a lot of the self-describing nature of that, as well as a lot of optimization that comes with this. But this would be, here you go, that's a file dump, and we've defined perhaps where you're getting it, and whatever research you're doing, we know it's at a point beyond whatever tap point we gave you, and it would be relatively big hand waving. Easy to bring back in depending on what you did and how applicable was to operations. So this is again back to the cartoon, right? So why have these like individual boxes? Why not just allow them all together? Well, for us, they're actually different services, and we do that because they're going to be reused. On ingest, we have a lot of different boxes out here depending on for every data source we're getting, right? you can't generalize that. You know, if you're reading from a database from Penn or from Duke, they're going to have their own nuances. But what comes out of that is our normal, and we talk one language, right? We're going to talk about these variables in the same way, same units, and that's where it enters our system. But then when we go into clean, this is the clean box, you want to deal with these problems differently. So for acute illness, we want every event. Right, so you look at that, if you think back to the standard I showed you, it's the metadata with payload. I want to get that every time there's an update every hour because I want to label that. With heart failure, what we're asked to do is to label on an encounter, not every event in that, but if the person is admitted after 24 hours of being in the hospital, we want to label. So for us, clean here is a record that shows all previous encounters or hospitalizations or outpatient care, whatever, for a patient going back to 2004 with a payload of data for their stay in the last 24 hours. So that's what clean looks like here, which is very similar to what we're trying to do with readmissions. There's kind of this, where we're starting to work through is these patterns that arise when we deal with longitudinal events to dealing with these acute events. And so we're finding that there's a lot of similarity between those, but as of now, there's a lot of choices that we're making for heart failure versus surgical readmissions. But here you go, there's this clean service, right? And you can imagine doing many things with that, where you might create features in the same way, but I want to detect when someone has heart failure. I want to predict the length of stay, which is hard to do as well. And I want to predict when they're readmitted. And this is something where I don't have to recreate this all the way back through, but I can connect into a single service there, which is a big benefit. And this stays true for each of these things as well. So I'm kind of getting to the end here. This is nasty to look at. This is still a cartoon, but it has more details. This is actually what we built. Here's all the different data sources. We have the different NoSQL Mongo repositories for each of those things, and then we merge them all together in a complete set. And then we do our clean process, feature extraction, the model prediction, and we have our external interfaces where we'll provide an API into these data sets and work out the access to them. And then alerts for the operational side and dashboards for the performance. But this is kind of a little, I organize these with a little thought, where this is our stack in MongoDB, Python, Pandas. GraphLab is an open source scaled framework. So think graphical constructs, but they also have tabular, but that they can be distributed. So where Hadoop MapReduce is used when you have something ridiculously parallelizable. But if you're going to do something where one job is dependent on the outcome of the other, like a PageRank, where you're trying to predict the importance of a website, and it's dependent on the importance of the other ones, it's horrible to use. And so this is a group out of Carnegie Mellon that came up with an approach for machine learning to scale and do complex algorithms at scale. So this is one that we're using when we get to that scale when we're bigger than memory on our laptops. And then this is how we kind of ship the data to researchers or partners to take a look at it and do it on a real-time API. This is maybe a chart to have you think about some questions that they might have. I'm sure I've forgotten things, but this is the world as I understand it in a lot of ways. There's really important research questions to explore here. I mean, how do you deal with missing data? What's the best way to compress these really high-dimensional representations of patients into these lower manifolds? This on the feature engineering side. Can we do deep learning well on this data set? Really exciting things, I think, to explore. The one that I have not seen much work on at all, and is both exciting and scary to me, is when we put these things out in operations, what the heck is going to happen? I mean, there's feedback that you're getting that you're not intending, right? So are we isolating ourselves from when someone thinks a patient is sick, they take their heart rate more? Do we want clinicians to have a vote in their actions going into our model? Do our predictions affect what we're measuring? It will happen. Those things are going to occur. We just need to address them as they do. There's not a lot of research out there that can guide the way. In healthcare, and this is something that that retail and advertising and DoD has been dealing with, but I think as it applies to healthcare is very, very unique. So that's the concept of it. That's the feedback. We talked a little bit about forecasting power versus human interpretation, and then creating model performance and human performance, understanding that design of a system. So a person, I have a likelihood of saving somebody, we should measure that, right? Given that I've done these things, there's a likelihood of outcome for the patient. And so there's a curve that you can put for clinical care, and how does that connect into what we're predicting and what can we expect from the whole entire system? So I think there's that kind of operational or design of a system that is definitely research worthy, and that we just have to explore it on the operational side. This is my final chart. I just wanted to open up for any questions that you might have.